Hi everyone, thank you for joining. So in this video, we're going to continue with Einstein's special theory of relativity. So now we've established the Galilean principle of relativity, which states that Newton's laws of motion are valid in all inertial reference frames, right? Reference frames that move at constant speed and on a straight line. Right. So now to move on to Einstein's theory of special theory of relativity, we need to think about a few things, and one of them is of course space, and the other one is time. So classically, space and time seemed like straightforward ideas. What is a space? What is space? So space, you just look outside, and whatever you're looking at it, that is space. And what is time? Time is an arena in which all these dynamical systems, all things move. It's like an arena, right, where things move in it, right? So this space, the definition of space and time, would be challenged by Einstein's rightly. So when we say relativity, I think the first thing that comes to mind, things like E is equal to mc squared, or black holes, or time travel, or a few paradoxes, right? But what is exactly, what is relativity in Einsteinian sense? Well, on one hand, the relativity is not a new idea, that we know the Galilean transformations, right? So what Einstein, one of his greatest achievements, I'd say that the relativity should apply to all the laws of physics. Yeah, I'll say here, not just mechanics. Okay, so that was his belief, yeah? So the problem here was the idea of relativity was incompatible with electromagnetism, especially the laws governing the propagation of light waves. Yeah. So this turns out that our assumptions about space and time required modification. Yeah. So this is where Einstein's genius starts coming into this picture. But we're lucky in the sense that you don't have to be genius to follow the footsteps of a genius, right? You might have the smallest garden in the town, but it doesn't mean you can't look at the endless fields, right? So, okay, so what is special about this special theory of relativity? Well, the special theory of relativity is a special case because we look at the motion at constant velocity, right, in which the acceleration is zero. This is why it's called special theory of relativity. Okay, so now let's talk about Einstein's principle of relativity. I think a good starting point is the 19th century, where the Thomas Young demonstrated in 1801 that the light is a wave. So, and then the big change, big influential thing in physics was that Faraday discovered the electromagnetic induction in around 1831, and this led to so many things, especially. But the problem here is if we call light a wave, then the first question that comes up is what is the medium in which it travels? So what is the medium? So if light is a wave, what is the medium in which it travels? Well, this was, I think, without an exaggeration, one might say, was the most important question of the 19th century. So, what is the medium? The medium in which light waves were assumed to travel is this thing called ether. But of course, what is this thing, ether? Can you take, can you put like collect some and put it in a jar or in a cup. Yeah, what is this thing? Right. Now, I think one of Maxwell's the greatest contribution was the his theory. Is he's predicted the light to travel at speed c, which is equal to 1 over square root of epsilon naught mu naught times 3 times 10 to the 8 meters per second. So this was, I think, Maxwell's astonishing, most successful part in Maxwell's theory. Yeah, and this is a very specific prediction. But the difficulty with such a specific prediction was that the implication of Maxwell's laws of electromagnetism are valid only in reference frame of the ether, this thing here. So that brings in, as you can see already, some problems when you consider the different reference frames. So in other words, what Maxwell was saying, that if you consider a reference frame, let's call it S, and we have this wave traveling at speed c, which is given here. So before Einstein, it was thought that the light travels at speed c in the reference frame of ether. Okay, that was the belief. But of course, now we are aware of relative motions. One would say immediately, well, if light is traveling at speed c in one reference frame, then if we go to S dashed, light will certainly travel at some different speed c dashed. Or, you know, if you're approaching to it, you might have some c minus v or c plus v. Depending on the reference frame, you could get things moving faster than or slower than the light. So the problem here, as you can see, that the Maxwell's theory did not obey the classical principle of relativity. There was just one reference frame, the reference frame of the ether, in which the laws of electromagnetism seem to be true. And to make matters worse, the fact that no one had been able to detect the ether meant that no one could identify the one reference frame in which Maxwell's equations worked. So that this led to two problems like that. You know, we're talking about a reference frame, but no one could detect ether, and nobody could ever seen or been in that reference frame. But more importantly, that the laws of electromagnetism seem to be true in this reference frame. So now we have a better understanding of the problem, that we can write down the principle of relativity. Okay, so what does it say? It says that all the laws of physics are the same in all inertial reference frame. As I've mentioned before, this name relativity is a bit ironic, because Einstein he was after absolute certainty where the laws of physics didn't vary, not only mechanics. But of course, this wasn't an easy problem to solve, because if you think about an observer here, okay, let's call this observer A, and another observer there, observer B, and again a cyclist. Okay, so cyclist here, who is traveling at velocity which is 0.9 c, right? So let's say the first observer and the second observer send light waves. According to, let me call this C, B and C, if you look at the relative motion, what we will have is the speed will be c plus v. right? So that's equal to c plus 0.9 c, which is equal to 1.9 c. As you can see, it's much faster than the speed of light. But if we look at AB, we will have c minus v, which is equal to c minus 0.1 c. 0.9 c, which is equal to 0.1 c. Yeah. The problem here was not so much conceptual. The problem was experimental. So let's consider an experiment that we have laboratory reference frame. Okay. So the experiment is that a photon is emitted at speed c relative to a pi meson. So that is, let's draw a pi meson here. The measurements find that the photon's speed in the laboratory reference frame is also c. In other words, we are not getting, as expected, we're not getting c plus 0.99975 plus c, which is equal to 1.99975 c. Okay, so the experiments show that that doesn't happen. You know, the measurements show that the photon speed in the laboratory reference frame is also c. And this is a very peculiar result, because we have this intuition now, the Galilean relativity. Yeah. And it seems like it is contradicting with that. Right, okay, so in the next video, we will talk about how can this be and how Einstein solved this problem. Okay, thank you for joining. I hope you enjoyed it, and I look forward to seeing you in my next video. Thank you.